If you were not in class when we did some notes and sample problems for 4.9, you'll want to go back and watch the previous video. Here we're doing your homework problems. So we will be able to do antiderivatives of any function that we've already done the derivative formula, but we're starting this topic with some simple polynomials. So we're using the power rule in reverse order. So we decided we could raise the exponent and then divide the coefficient by that exponent. So this would be a 4x. And the negative 4 term, we would raise that exponent to a 1, but clearly you know that negative 4 would be the derivative of negative 4x. And then we know that there could be a constant on that original. So we'll put a C1 here since I'm going to do a second antiderivative. And then can we find C1? Yes, we can, because we're given an initial value on f prime. We know that f prime is equal to 30 when x is equal to 2. So we can do a little arithmetic here. So it looks like we've got 32 minus 8. So that would be a 24. So our C1 value would be 6. So now we're finished with our f prime, our first antiderivative. So now we can repeat, do the second process here to go backwards to f of x. So we'll raise the exponent, divide by 4. We'll raise the exponent to 2 and divide by 2. And this will be a 6x, and then we'll have to do another constant. Now, you might use C for your first part and D here. I don't know why I use C1 and C2, but you could give them any variable name. And can we find C2? Yes, because we are given an initial value here also. F is equal to 8 when x is equal to 1. So fairly quickly here, it looks like we get a 3 for C2. And we're not quite finished with the problem. So let's clarify now that we know our function is x to the 4th minus 2x squared plus 6x plus 3. But our question says to use the function. Now, why would you ask that? Well, because this would make a perfect multiple choice question. Remember, we don't want you to be able to do a multiple choice question backwards from the answers. So if you substitute here, so we're putting in negative 1, but for these even terms, they'll stay positive, but this odd power will stay negative 6. So let's check this out here. We got negative 8 and positive 4. So it looks like we'll come up with negative 4 for our y coordinate. So that would be a good multiple choice question. All right, the next couple of problems I've given you the answers. So would you please try the problem if you haven't already? Pause the video before you listen to the solution. See if you can come up with it on your own. All right, so let's think what we're given here. A car is traveling at 50 miles per hour, so we're given a velocity, and it applies the brakes, producing a constant deceleration of 22 feet per second squared. So we're also given an acceleration rate. What is the distance covered before the car comes to a stop? All right, well, give it a try here. So working backwards, we know the acceleration is always negative 22 since you're decelerating. So let's work backwards to find our velocity function. So negative 22t plus some initial value c. That would be what you get when time is 0. So instead of calling it c here, I might call it initial velocity. And notice here that we think, oh, initial velocity was given, but be a little careful about the units here. So notice the deceleration is in feet per second squared, and our velocity is in miles per hour. So you better make your science teacher proud here and do some cancellation of units. So what do we want to do here? We want to get rid of miles. So let's multiply by 5,280 feet. And we want to get rid of hours. So there's 60 minutes in an hour and 60 seconds per minute. So can we go right to seconds here? So let's see, you could grab your calculator, but let's see what I can do here. Divide by tens. This number I bet is divisible by 12. Let me give it a try here. See how I think that 48 would leave a 48. So I think that's going to be a 44. Not so bad. 5 times 44 is 220 over 3 feet per second. All right, if my arithmetic is correct, now we know that that is our initial velocity. All right, in feet per second. All right, now let's proceed. What do we want to do with this? We want to know the distance covered when the car comes to a stop. Well, I can't tell you that yet, but I can already find out, when does the car stop? When does the car stop? That's the same as asking where v of t is equal to 0. Where is v of t equal to 0? The velocity reaches 0. This has a nice factor we can get out of there of negative 22. So I think we can see that the car comes to a stop after 10/3 or 3 1/3 seconds. But that's not the question. The question isn't when does it stop, but how far is it traveled? So I think we have to do another antiderivative before we can answer that question. So let's find our position function. We'll raise the exponent to a 2 and divide by it. And we'll have this constant, that's a 3, clarify that, in front of a t. And then an initial position here as our constant. Well, think about this. When we apply the brakes, we want to know how far does the car travel before it stops. So we really only care about the distance between these 2 points. So no matter where you are on the highway, we don't care if you're 10 miles away from home or 1,000 miles away from home. We can consider this. We can shift this to the origin. So regardless of where it is, we might as well say that S sub 0 is at the origin. So I'm not going to put a constant there. I'll just use that as 0 point, our initial origin. So now what do we need to do? We know that we're going to travel 10/3 seconds. So all we need to do, and you can grab your calculators and approximate this. So we just want to put that value into our function and do some calculating. And in exact form, I have 1,100 over 9 feet. You could round that off into decimal form if you prefer. All right, let's try another one. A custard pie is thrown vertically up from the ground. Well, that sounds kind of fun. It has an initial velocity. And what do we know? Again, it doesn't say we're anywhere else, so I think we have to assume that we're throwing the pie from ground level on the planet Earth. So we know our acceleration constant when we're working with feet is negative 32. So you will quickly get used to this, and hopefully now you appreciate knowing where these constants, where this negative 16 came from in all of those algebra textbooks. We need to add an initial velocity, and we are given the initial velocity. And then we can find our position function, another antiderivative. So we're going to raise the exponent to 2 and divide by it, put a 48t, and then our constant here, which we could call our initial position, And of course it says ground level, so that's the same as saying that at time 0 the height was 0. So if you put 0 in for t, of course, then this is the initial height. When you put 0 in for t, the first two terms disappear. So this is the initial position at time 0. And it is ground level. So that constant would just be a 0. So this is our position function, and this was our velocity function, and we started out with an acceleration function. All right, now let's see what we need to do here. Find the greatest height that the pi attains. So it is going to reach its vertex. When is velocity equal to 0? That's when the pi stops and heads back towards ground. So you don't have to show this. I think you guys can all see that that's going to be after 3 seconds. That's when it reaches ground level. So now we have to find the position. How high was it at its maximum height? So we want to calculate here, 3 squared. Get a little bit of room here, plus 48 times 3. Oh dear, this negative sign just caused me some grief here. I don't think I like the looks of that. And where did I make my mistake? Oh dear, I think it's way back here. Look at what I did. I changed this value too quickly. What's the antiderivative of negative 32? That should still be a 32. My apologies here. All right, so that's going to change things a bit. Let me rework some things. What else do I have to fix? All right, so now let's go back to position. My apologies. This is where I'm dividing by 2, so I got one step ahead of myself. So that should be a negative 16. Maybe we're not too bad to fix my mistake. All right, but now let's repeat what we were doing. We want to find out when is the velocity equal to 0. So I want to set this equation. So it's going to change my answer a little bit. So 32t equals 48. 48 over 32, those are divisible by 16. So we get 3/2 seconds. And now we can find out what is the maximum height. So that would be the height at 3 seconds, or with your calculator 1.5. Your choice. All right, plus our 48t plus our 48 times 3/2. And that is not negative. That is a positive 3/2. All right, so you could do that arithmetic or grab your calculator. And I think it's going to, if my notes are correct, be 36 feet. All right, sorry for that, slowing you down there with that mistake. All right, let's do some graphing. This is the graph of f prime of x. So can we think what the original function would be like? All right, so we've done this before, so let's think about this. Our first derivative is positive here, so that means f is increasing, and then our derivative is negative, so when the derivative is negative, f is decreasing, and then our derivative is positive, so f is increasing again. And think what else we can do here that would help give us the shape of the graph. Our first derivative is decreasing all the way from here to here. So remember that when f prime of x, when the slope is decreasing, that is the same as saying that f double prime will be less than 0, which is equivalent to saying that the original function is concave down. And then on the other side here, the slopes f prime is increasing. F prime increasing is the same as saying that f is concave up. So that all helps me to graph. But notice that we don't know we don't know the constant. We don't have an initial value given. So we know the basic shape of the graph, but we don't know where to put it. So we can start at any value you want to. So think what you know here. So concavity changes. So we have to have, at 0, we have to have an inflection point. And f is increasing and then decreasing. So we have to have a local max here. And decreasing to increasing, we have to have a local minimum there. So this is going to look like part of a cubic graph, but we don't know exactly where to put it. So the places where f prime is equal to 0, those are the places where we have to get our horizontal tangents. So our graph is increasing. So I could start wherever I want to. So for example, if I started up here, f is increasing, and then f is decreasing. And concave down all the way till we get here. And then it's still decreasing, but concave down. And then here where we have our horizontal tangent, and then it's going to increase again. So notice that it's got to be something like a piece of a cubic graph. Our inflection point for my graph happened to seem to land at the origin. But let me redraw that because we don't know exactly how steep to make that. So I might have exaggerated here, and I could put it any place that I wanted to. So I could start way up here and say that there's its turning point. And then it has its concave down, and then it has its inflection point, and then it goes back up. So we don't know. We could have that graph anywhere along here as long as it has that same basic shape. All right, so here's another one I didn't quite get all within my screen. We want to sketch a function on an interval, a closed interval from -2 to 2, such that the initial point, the intercept point, f of -2 is 0. So at -2 on the x-axis, we want to be at 0. Oh, and was this directions for the previous problem? I have that on a strange place on my graph, or on my assignment sheet. All right, well, let's go back up. That's interesting that I interrupted that. So let's go back and redo that next one. So all that's saying here is that we want to, I thought I was doing a brand new problem. So all it's saying is that at -2 we want to start here on the axis. So they're giving us an anchor point. So they're giving us an initial point to start with at -2, 0. Okay, but it's the problem we just did. So I want to be increasing until I get to 1, and then decreasing, and then inflection point, and then back up again. Okay, so again, I don't know exactly how steep to make this, but we know it has its horizontal tangents at -1 and at +1. Okay, sorry, I was not realizing that that was all part of question 4. So you got more than you bargained for. All right, let's take 5 apart step by step. So we want a function f that contains 0, 0. F of +2 and f of -2 are both at 1. F of +2 and -2 are both at 1. And f prime of 0 is 0. So we want a horizontal tangent at the origin when f prime is greater than 0 for everything on the positive side. So f prime is positive means that f has to be increasing over here. F prime is negative on the other side. So if f prime of x is less than 0, then f is decreasing on this side. And our second derivative is positive when the absolute value is smaller than 2. So absolute value means from negative 2 up to positive 2. Our second derivative is greater than 0. So that means it's concave up the whole way here. So all the way across from negative 2 to positive 2, we want f to be concave up. All right, and then when the absolute value is bigger than 2, then f double prime is less than 0. So I went a little too far here with my lines. This should just go up to 2. And then after that, we should have concave down. So outside of that, we want concave down. All right, and we got a little bit more. The limit as we go to infinity and negative infinity is 2. So this is a horizontal asymptote. The left and the right end behavior. So y gets very close to 2. So let's make a horizontal asymptote on our graph. So do you think you're getting a visual picture of a function that works here as we talk through this? Okay, so we need it to be concave up. We need it to be concave up here, increasing, and concave up here, but decreasing. And then we need it to be concave down and approach that asymptote. Concave down and approach that asymptote. So I think that would be a graph that would work. And one more, number 6, we're given a graph and we have to analyze what we know here. So increasing, this is f prime. This is the graph of f prime. So for question A, f is increasing when f prime of x is greater than 0. So that would be on the interval from x1. And here's where you can do closed endpoints if you wish. x1 to x4, we have a derivative of 0, but then it's positive again. So remember that this would mean that f is going to have a saddle point. F has a saddle point because it has positive slopes, 0 slope, and then positive slopes again. So it temporarily has a horizontal tangent, but then it continues right on. So we could do this all as one increasing interval from x1 over to x5 for increasing. Now remember that we now have to put an equal to there. So f prime of x is greater than or equal to 0 because we do have one place there with a horizontal tangent. All right, our second question is, where does it have a local max or local min? So our first derivative changes from negative to positive right here. So f has a local min at x1 at x equals x1, since f prime of x changes from negative to positive, but it never crosses over the axis anywhere else. So it has again, it has that bounce point here. The first derivative bounces, so f does not have an extrema there. Our next question says, on what intervals is f concave up? So concavity is when the second derivative is positive. Well, when would the second derivative be positive? That would be when f prime is increasing. So f is concave up when f prime of x is increasing, because then f double prime of x would be greater than 0. You don't need that parenthesis. So f prime of x is increasing on two different intervals from x sub 0 to x sub 2 and from x sub 4 to x sub 5. If I'm reading those subscripts correctly. And then it would be concave down when f prime of x is decreasing, because that would be where the second derivative would be less than 0. And that would be between those two values. So that would be from x2 to x4. So this is definitely practice we've done before. Coordinates of the inflection points. So concavity changes here. We can see that concavity changes at x2 and at x4. So f has inflection points at x equals x2 and at x equals x4. And you can say, since concavity changes, when f prime changes from increasing to decreasing, or vice versa. Now you might say, how come you didn't just say where f double prime changes signs? Well, because we don't see f double prime. So when we're looking at a graph of f prime, all of your logic should come from f prime. So instead of talking about the second derivative, which you can tell from f prime, you still should stick with f prime in your justifications.